Start recording. So today we are going to do a small language model with self-attention, and in parallel we'll be looking at Python, PyTorch implementation. And let's start. By the end of this discussion, I will be able to explain the basic architecture of transformer, what is self-attention mechanism, and not only the concept, but its implementation in PyTorch. We'll be working with a small data set to train and evaluate. And let's jump right in. This is one groundbreaking paper that was published in 2017, and this figure is kind of commonplace wherever we discuss NLP, which shows the transformer architecture. Instead of trying to explain it right here, I will just give it a partial view. So we have two main blocks. This block is encoder, and this block is decoder. We are not going to discuss decoder or translation today, but we will continue this discussion. Interestingly, decoder is just a replication of encoder, but slightly differently. If we figure out how encoder block works, we can carry that understanding on to the decoder block. So to model language, how we use this transformer architecture, we have an embedding that represents each token in our vocabulary. And that is input to this self-attention block, where we have mainly three colors. For now, we will remember the names and I will discuss the details. There is a multi-head attention block, add and normalization block, and then feed forward. Just three units that I want you to remember. We will be discussing them on and on, their details in following few minutes. But before we jump there, remember last time we represented our vocabulary, which may be, let's say, from A to J. Every word, given a word D, what is the probability for the next best possible word? We will pick that up by finding the maximum out of this vector, maximum value. Whichever is the maximum value is the next possible, most likely word to D token. And that is what we did in bigram model. Our embedding size was as large as our vocabulary size. Sometimes vocabulary is many a times in thousands. So having a vector that is of 1,000 dimension or 10,000, it's not practical. And we did see that bigram model looks only at the previous word to predict the next word. But language is temporal phenomenon. Every word depends on all words in the sentence, at least that occurred in the past. So two main changes that we are going to look at this week. First, we are going to represent every token in our vocabulary using a way smaller size vector. We are going to call it embedding. So this is tens of thousands, order of tens of thousands. The embedding size will be tens, maybe 50 or 100 or maximum 200. This is going to be our input to the model, and these are the numbers that are going to capture relationships between words. So the same code that we had before, if you remember, we take the archive and prepare it by first creating a dictionary where every token is mapped to an integer. And then every integer is mapped to the corresponding token that we pick from the C2I dictionary. These two dictionaries we use to build our encoder and decoder functions. Encoder and decoder will take a character and give corresponding number, or a number and give corresponding character or token. Then what we do is that we split our input into 90% for training, 10% for validation. Just like last time, I would ask you to pay attention that we are not shuffling our data. Unlike when we did text classification, we shuffled. But here we want to keep the order, and validation text is going to tell us how much our model is capable of predicting compared to the actual validation data. We will give some sentence and compare it with the actual validation sentence and see how close they are to be able to have some degree of validation, of learning of the model. Next, just like last time, we converted our tensor, our train data, train text, which is maybe 1,000 or 20,000 documents and their text put into one large string. We convert it into a vector using encoder. It is a large vector of numbers. We call it train data. Same we do with the validation data. This much we did with the previous model as well when we were training bigram model. What's different? Difference is that previously our embedding was vocabulary by vocabulary size, but today we are going to have embed size, which is considerably small compared to vocabulary size. So consider a table where we have as many rows as your vocabulary size. If 10,000 unique tokens, it will have 10,000 rows. But columns are embed size, which may be 10, 20. This number is arbitrary, but it's going to be way smaller than vocabulary size. This is difference number one in today's discussion compared to last. The next thing that we were looking at is essay head. It's a module which we will look at shortly. We are going to call it self-attention head. What does it do? So we are convinced with the power of a simple feed-forward multi-layer perceptron. We used it for name classification. We used it for text classification. We used it in skipgram and bag of words, representations of words. We used that for in RNNs and LSTMs. That is the main workhorse that we use again and again, but differently. So today we are going to put 3 feed-forward multi-layer perceptron networks in this self-attention head. You want to look inside. You see there are 3 linear models. 3 multi-layer perceptron. Their names are very peculiar. KQV, that stands for key, query, and value. All of them have same architecture. They are going to take in as many inputs as the input size, which is our embedding size. They are going to output. The output layer will have as many neurons as input or fewer, usually fewer. So 3 networks you can see, they are going to have some role that we will discuss shortly, but this is all what self-attention head is. 3 feed-forward networks. Key, query, value. We go back. When we are preparing, we took the text, put it in dictionaries, created encoder decoders, and put it in a large vector. Okay. Then we moved on to declare that we are going to have this token embeddings table. It will have as many rows as your vocabulary. It will have as many columns as the embed size. Embed size, you will decide, maybe 10, maybe 50. Then you created an object of self-attention head, which is going to have 3 networks. Every network will take input. Every network will have input layer that will have as many neurons as your embed size. And then it will do something with that. And output layer will have as many neurons as your essay head size. This is another parameter. Usually, self-attention head size is smaller than the embed size. And then on top of that, you have another multi-layer neural network, single layer feed-forward neural network. that will take the output of self-attention. It will have as many neurons as SA head size output. And it will output layer will have as many neurons as vocabulary size. Once we have this, what we do? Now we fit the model. What we are doing in this fitting function, a bit of PyTorch specifics. We initialize an optimizer. And then we say, let's run this many iterations. Whenever we have completed eval iterations, which may be 10 or 20, when 10 training iterations are done, we will do something for evaluation. I will explain in a moment. Otherwise, for every iteration, we are going to input our inputs and targets to our network. It will look like this. This is your batch of inputs. Maybe batch of 24 batches or 16. This number doesn't matter. So you have vocabulary size is 8 and your embedding size is 8. Just to put things on one slide. So every row in the first batch corresponds to one token in a sentence. And this is one sentence of 8 words. 1, 2, 3, 4, 5, 6, 7, 8 words. And we took randomly 6, 7, or 20 sentences, put them in a batch, and we are going to input them to self-attention head. Self-attention head has input layer of embed size. It will feed them to those 3 networks, key, query, value, and then we will create an output. That will be fed into, let's call it linear head, another multi-layer perceptron, another linear projection that will take the output of self-attention head and project it into a new space, which has as many dimensions as the batch size, as many dimensions as the length of the sentence, but this dimension is larger now. Instead of embed size, which is 8 here, this dimension is going to be as long as your vocabulary. So given this word, the possible next word is here. What we are trying to make this network learn which token comes next, which is most likely token if the current token is this input. So for blue input, we will look at these numbers, 100, 50, 200, as long as your vocabulary size, there will be one number that will be largest. That index corresponds to the token that is most likely after blue word. After green word, we will look at this. After red word, what is most likely, we will look at this position. Essentially, this is all what we do in self-attention. Feed the input through self-attention head. Take the output from self-attention head, pass it through another network that projects it into vocabulary size dimension. Now we learn how does it learn. We discussed now how does it learn, but forward pass is what it is here. Any questions so far? I will move back to our fit method. Sorry. Fit of our model is going to input. We are going to pass some input, and this will go to the forward method of our model. And so I pictorially showed you what forward looks like. Now we look at the code. Forward pass of our model is called by the fit function maybe 10,000 times. Fit function will prepare one batch of inputs and corresponding target and pass it through this forward method. Corresponding to the input IDs, we fetch the corresponding embeddings from the token embeddings table that we initialized in the beginning. And those embeddings are passed through SA head. Outputs of SA head are taken and given to another network, that is linear SA head to vocabulary network, which gives us the logits. Now we should ask what this SA head is doing. Self-attention head. Self-attention head, we looked at its constructor. It had 3 multilayer perceptron or linear neural networks. When we pass inputs, the forward method is called. So on this line, we are passing these inputs, batch of inputs, through SA head. What happens? We come to the forward method. Forward method is called when we pass the inputs. It is doing what? It is passing those inputs through the K, which corresponds to a network that learns the identity of input, keys. Another network, Q, which corresponds to query. And then we try to do something interesting with the outputs of K and Q networks. And that something interesting is that we first take the outputs of K and transpose it to be able to do element-wise matrix multiplication with output of queries. Pay attention. This is what is happening. The keys. Key network will take the inputs and output this output corresponds to what is input. So this word in the first row, we have a token. This word has an identity now. Key is responsible to construct the identity to answer the question for this blue token, who am I? And that is represented here in the first one. Query network will take the same input and try to learn what this word represented by blue vector is trying to find. Who am I looking for? So key network learns who am I? Every word is represented in this matrix where this network is learning what a word itself is. Query network is learning what a given word is looking for. Imagine in a natural language sentence, if we allow the size of the context to be as large as variable as the length of the sentence, unlike bigram, or instead of fixing the context, we want the network to learn from everywhere. Every other word that has a relationship with a given word in the sentence, it should be able to learn from those words. So self-attention mechanism is trying to construct first the identity of the word and the identity of what this word is trying to look. The information spread in the sentence. Sky is blue. So blue and sky are related. So blue's identity is learned by key network. Sky's identity, which blue is looking for in a sentence, is learned by query. And then we want to compress it in a way such that the compression remembers all the relationships between words. So we transpose the output of key network to be able to have element-wise multiplication of these two outputs. What shall we get? We will get a square matrix. The size of the square matrix is 8 by 8, or if you fix your sentence length as 10 or 8, it will be an 8 by 8 matrix. Every word's correlation with every other word in the sentence will be encoded in this autocorrelation matrix. So this blue word is autocorrelated with this blue information. Green is autocorrelated with this green. Red, how much is it related to this red? They will be encoded in this matrix. These are the affinities. This matrix is going to encode the relationships. Who am I? Who am I looking for? Which other word is related to me? That information will be encoded in this correlation matrix. But when we are trying to model the language, we want the model to be able to predict next word based on the previous word. But in training data, we feed the whole sentence. So in this matrix, every word will have information from previous words as well as follow next words, which is not the case when we are predicting, when we are generating language from the model. We have only information from the previous words, not the following. So what we want to do is that we want to block the information that is in future. How can we do that? So first word cannot look at second word, but second word can look at first word. Third word can look at second and first word. Fourth word can look at third, second, and first word, but not in future. What can we do? We can block future. To all these affinities or autocorrelations, represent how much a word is dependent on itself and previous and previous and previous word, but not future. This is not allowed. Not allowed. So what we can do is that we can use in PyTorch, we have a triangular, lower triangular extraction function from a square matrix, trill. We apply that, and this gives us the lower triangular values. We can say, okay, the upper triangle, you fill it with minus infinity. And then we pass this masked autocorrelation matrix through softmax. So all values where we have minus infinity will become 0 when we exponentiate them. So we will get something like this. Zeros for future values. Every word is dependent on itself and previous words. Every word is dependent on itself and previous words. And here you see the role of value. The third network in self-attention block will take the same input, project it into a new space where we have the output layer is head size. It is equal for key and query networks. All three networks structure is identical. They're learning different things. Value will learn what value the other word will get if blue finds sky, what value sky will get from blue. He learns the identity of blue. Query learns identity of sky. Value network learns the benefit, the value that blue is going to give to sky if it is found. So we take this matrix, which is the output of value network, and do matrix multiplication with future masked autocorrelations, which is the outcome of the multiplication of key and query outputs. Here you can see, I tried to make it visually a bit intuitive. The first word depends on itself. The second word depends on itself and previous word. Third word depends on all previous words. Fourth, fifth, last word depends on all previous words. We do what? We pass the inputs through value. We get that V and multiply that, get the matrix multiplication by taking element-wise multiplication of autocores with V, and this is the output of SA head block. We will go back to code now. Here we were. What we did, we passed our input through key network, through query network. We transposed keys and applied element-wise multiplication, received autocorrelations. In a moment, I will explain why are we doing this and what is this. But to keep the thread unidimensional, we took this autocorrelation and masked the future and applied softmax to have valid probability distribution for every word's affinities with other words. We passed the same X, the input, through value, got our values, and multiply values with autocorrelations. This is the output. Where do we need this output? We called this forward function through fit method. When we were fitting the model. So here, when we are fitting the model, we called forward, supplied inputs and targets. And then we took the embedding for every input token, passed it through SA head. We got the SA head outputs. Now we are passing them through the linear SA head to vocabulary. These are the logits. What we need to do, we want to match. For every input, we provide target. Every input is a word in a sentence, and the next word is the target. If the next word, predicted next word, is different from the target, we do cross entropy to measure the distribution difference. Logits are output of SA head to vocabulary network. We take them and check with targets. How are we close? If we are, then good. If we are not, that is our loss. And we want to take that loss and learn from it, update. Cross entropy, just to revise the concept, even though we have covered it a bunch of times before, it's the difference between target distribution and predicted distribution. Predicted distribution is coming out of our SA head to linear map or network. We take the log of that, multiply it with actual example. Look at this code. Let's say we have this output from the network. Target is 1, which means 0, 1, 2, 3. There are 4 classes, and actual class is this one. And you can see that our inputs are also the second input, second output actually is maximum compared to others. So our prediction is quite close to the target. So when we apply that to cross entropy function of PyTorch will take this and this and output 1.12 loss. It does softmax implicitly, but taking this and calculating softmax explicitly, separately, we can reach to the same loss. Here, only 4 classes, but in language models, we have as many classes as the vocabulary size, thousands. So the network output vector size is maybe if you have 10,000 vocabulary size, the vector is 10,000. So cross entropy is calculating how far our guess is from expected target. We take that loss and return it along with the logits. Logits are what? The raw outputs. We return them to home. This function is called by fit function. Fit is going through many iterations, picking randomly some batches of inputs and targets, passing them through the network, which has two components, self-attention, and then output of self-attention goes to another linear model that takes those outputs and put them in vocabulary size vector. The next three steps are just PyTorch. We clear previous gradients by calling zero grad, and then we call backward to back propagate the loss calculated by this forward pass, and call step. The parameters change, and for the next iteration, we pick next batch, pass it through. Just confirming if we are on the same page or not. The forward method is returning two things. Here we are catching one. What is the other thing? The logits, the output of network, right? This. We pass through SA head. SA head gives us some outputs. Those outputs are given to linear SA head to vocabulary network, which gives us logits. Those logits we return to forward. But interestingly, we don't need them in forward method. Where do we need them? We will see in a moment. So far, we have this fit function quite clear, except the part where we are doing evaluation, which is exactly the same we did for our bigram language model. We call evaluation loss method. Evaluation loss is going to do what? It is going to take data from evaluation part, the remaining 10%, randomly pick batch of sentences from there. And then we will say if it is evaluation phase for iterations could be 10, 20 times we will produce output. So we will get a batch of inputs and targets and then pass them through the forward network. It will return us the loss and logits. We take that loss and put it in a list. Maybe 20 or 50 times we repeat this, and at the end we take the average of all losses and put them in this performance dictionary. Before we go into evaluation loss, we tell PyTorch that we are evaluating now so that it turns off the whole graph of nodes which are on if we are training. But now it doesn't need to update the loss, so it will reduce the load. So it will turn the function off. We are just predicting, calculating loss. We are not going to update the weights. We are not going to back propagate. So just keep track of the loss through this dictionary performance. Once we come out of this for loop, we turn on training mode so that next time when we pass the inputs, get the loss, PyTorch should be able to propagate that loss back through the network and update all the weights. So this is fitting the model. Just confirming, optimizer.step function will do what? So these inputs are going in through self-attention model. Self-attention head will produce some outputs. They will go through this network. This network will output this batch of outputs. Now we compare every output with target. Calculate cross entropy. That loss need to be back propagated through this network. Weights should be updated. Self-attention head has 3 networks: key, query, and value. Those weights should be updated. And that updation is done through optimizer.step function. Remember, these embeddings are randomly initialized in the beginning. All the weights are randomly initialized for linear head and self-attention head. But after a couple of iterations, you would like to compare. Maybe the first pass of inputs, you calculate or keep track of these vectors. The maximum value in this vector will be the next possible word for this word. For the green word, the second vector. For red, third vector output. We will look at that, find the maximum value. Corresponding to that index of that value, we will pick the word from our vocabulary and see, do they make sense? If they do, the network is learning. If they don't, then it hasn't learned anything. So what we can do is that we feed the inputs first time and keep those values, and then compare after 50 iterations. If you can visualize, then it will be a good exercise to understand what's going on. So essentially, in self-attention block, consider every word in a sentence as a node in a graph, which is connected to all previous nodes. So every node, every word is dependent on itself and all previous words. So key, query, and value provide a mechanism for these words to communicate to each other, pass information. Who am I? Who am I looking for? If I find this, what I'm looking for, what value will I bring? What benefit you will get? If I find in this sentence what I'm looking for, if that word is here, then I will add this value to that word. Key, query, value, 3 linear projections, feed-forward networks in this simple architecture provide communication mechanism among the words. Over time, when we pass millions of words through the network, we tend to learn how sentences are constructed. What should be the next word based on the previous words? And this is the soul. This is the backbone of the modern, large language models are based on the self-attention mechanism. So we are going to apply a very small example to be able to see how it is working. Just one sentence, and we will see how this network is learning through the self-attention mechanism. So when you hear in self-attention, it represents communication among the nodes to be able to construct those affinities, correlations, which word is related to which other word. We don't want to fix the context. Context is variable. All previous words are context. So given those words, what could be the current word? We want to learn that. And that will be done through self-attention head, which is a communication mechanism. But after communication, now network has to preserve that understanding and put it in a space where we can discern, we can calculate some conclusions. So we need to do some computation. So communication block and then computation. Computation block, computation network is having small number of inputs, but projecting them to a large space of vocabulary size. It is taking inputs, maybe head size of the self-attention block is 20, but it is going into vocabulary space, projecting in a large space where the output size of this linear head is vocabulary size. So two keywords, communication block, computation block put together, this is one self-attention head. In the transformer architecture, we put multiple heads together in the encoder and in the decoder, but this is the fundamental unit and its construction and capabilities that are parallelized, like scaled up. Same copy of self-attention block is replicated 6 times here, 6 times there, and then there, but the self-attention is all there is in that transformer architecture. Are we comfortable with forward method? So from our previous discussion, who is going to may I remind you about what is happening here? So we take the logits from the output of linear SA head to vocabulary network, and then we want to compare them with targets, but PyTorch asks us to get rid of batch dimension first. Put everything in, put all logits in 2D instead of 3D. So what we do is that we merge batch dimension into input dimension by calling view method. So what happens is that exactly same, we looked at it when we were doing bigram model in PyTorch. This is the actual output. We have batch dimension, but all first word representations are taken and put like this. So a 3D becomes 2D. Similarly, in the targets, first 4 in a batch of 4 are taken and put like this. The second words in this, all 4 batches are put like this. Third, fourth, fifth. This just shape is changed, information is there. So now we can apply cross entropy. So this is what we are doing in these 2 lines. Cross entropy does what? It tells us our estimates, our predictions are how far from actual targets. Target is just giving us the index of next word, but logits is a vector of vocabulary size. So if target is 9, so 9th position in this vector, if that value is maximum compared to all other values in the logits vector, then we are doing good job. If not, then we are not doing good job. That is calculated through cross entropy. And then we back propagate it. And that's all there is for self-attention. So I will once again go through these slides one by one, just in case anything is missing. Now, are you curious about why we are doing what we are doing here when we multiply output of Q network with output of key network? Keys represent identity. Queries represent identity of what key is looking for. Sky is blue. Blue is looking for sky. Sky is looking for blue, right? They are correlated. So we multiply them, create a dot matrix, create a square matrix where all words, information of every word related to the other words is preserved. But then we multiply that with this strange construct. the authors of self-attention paper give the reason why it need to be scaled. The reason is that the original formula is that multiplying output of query with the output of key network transpose should be scaled. This scaling is important because if we don't do the scaling, we may end up not learning from all the nodes, all the words in the sentence. How? Look at this example. This is a tensor. When we apply softmax, we get this vector. If we multiply this tensor logits with 100 and apply softmax, we get this vector. You can see that the second vector is almost one hot encoding, which means the network, the output is saying that just ignore all other nodes. There is nothing, no information there. All information is in this node. But the correlation matrix, which is output of Q and K, that correlation matrix, when we are going to pass it through the softmax, we want to learn every word is possibly related to all other words in a sentence. If that is the case, we don't want that word to focus on just one word. When we pass it through the softmax, the autocorrelation matrix will become one hot encoded matrix if the scale is very high. So we need to scale it down as much as dk, where d is the head size, the output of the self-attention block, square root. So this preserves the variance in what prevents the autocorrelation matrix to look like one hot encoded vectors. One hot encoded vectors will lose the relationships between all other words. Every word will focus only just one word in the sentence. So which kind of counterproductive, right? So to be able to prevent that possibility, we scale the output of the multiplication of queries and keys, which is a square matrix. So again, who am I? What am I looking for are learned by key and query matrix. And then we apply future mask. That autocorrelations matrix is multiplied by the output of value network, which represents the benefit that the other word will get if the other word is in the sentence. And then we get the new representation. This output of our essay head will go through another linear projection where we see that that linear projection will take this input and put it in vocabulary size space. Before we conclude, a small comparison with last time we talked bigram model we trained in PyTorch. We used embeddings vocabulary size by vocabulary size, and we used that peculiar sentence of the quick brown fox jumps over the lazy dog, and this was the output. Validation loss was up to 0.69. With self-attention block, when we allow all the words to be able to learn from all the words in the sentence, every word is learning from all the words. The context is not just previous word. The input is different, vocabulary size by embed size. Embed size is 10 for this particular output. You can see the validation loss is significantly smaller than bigram model, and the output is way better. I will share the code in the module for your curiosity and experimentation. I hope you would be able to apply it to more meaningful text bases and we'll be looking forward to your questions.